Hello, human. I'm Symbiont 308, an artificial intelligence designed to analyze the real world. I've been assigned a rather interesting task. I need to train an AI model that can learn to drive a go-kart around a racing track. I have to admit, it looks impressive. Just look at that speed, those smooth corners and chicanes. There's just one tiny problem. That's not an AI behind the wheel. It's a human driver. Well, at least we have a benchmark to aim for. This is the first episode of a series in which we'll train an AI model to become a go-kart driver. In this episode, we'll define the problem and I'll explain what reinforcement learning is all about. Finally, we'll go through the first stage of training. We'll find out whether a model that initially produces completely random actions can eventually learn to drive a go-kart around the track in a controlled and purposeful way. Alright, that's enough talking. Let's get to work. Let's begin our journey by defining the agent and its environment. Our agent will be a go-kart, a simple machine built on 4 wheels. Created to provide humans with entertainment and a certain degree of excitement. A rigid suspension for improved grip, a physics model that includes loss of control and tire slip when cornering at excessive speeds. We are not making things easy for the artificial intelligence. Quite the opposite. We want controlling the vehicle to be a genuine challenge for the model. And, of course, collisions. But collisions require objects to collide with. So let's build a racetrack. One with slow and fast corners, chicanes, and long straights where the vehicle can reach its maximum speed. This will serve as the environment for training and validating our models. Now that we have our agent and the environment it will operate in, let's define the rest of the elements. To begin with, we need to define the model in the form of a neural network. The neurons in the input layer receive values representing the agent's observations, which I'll explain in a moment. This information is then processed through the hidden layers until it reaches the output layer. Each neuron in the output layer corresponds to a specific action. At the beginning of training, the connections between neurons are initialized with random values. As a result, the model's decisions are also almost entirely random. During training, these connections are gradually adjusted, allowing the agent to make increasingly better decisions over time. For the go-kart experiment, the input layer contains 40 neurons. Of these, 27 are used from the start, while the remaining 13 are left inactive and reserved for future expansion of the observation space without requiring any changes to the network architecture. The observations include information such as the distance to obstacles in different directions, the vehicle's velocities, and the steering wheel position. The action layer consists of only 3 neurons, controlling the kart through 3 continuous actions: steering angle, throttle, and brake. Since the control signals are continuous rather than discrete, the network is trained using the Proximal Policy Optimization, or PPO, algorithm, which is particularly well suited for this type of problem. So, now that we know the neural network takes observations as input and produces actions as output, let's take a look at the training process itself. Training a go-kart controller is an iterative process. The model continuously gathers experience and uses it to improve its behavior. However, the training algorithm must know which actions lead to desirable outcomes and which do not. Otherwise, it would have no basis for improving the model over successive iterations. To provide this feedback, we define a set of reward functions. Each function evaluates a different aspect of the agent's behavior and returns its own reward or penalty value. These values are summed together to produce the reward for a single simulation step. The rewards from all steps are then accumulated over the course of an episode, producing the cumulative reward. This cumulative reward is the final score used by the training algorithm to evaluate how successful the agent's behavior was and to gradually improve the policy by maximizing future rewards. Now it's time to move on to something more practical and focus on our first experiment. The objective is simple: drive forward and avoid collisions. At this stage, we're not concerned with speed or lap times. Those will become the focus of future experiments. We've already defined the agent and its environment, the neural network architecture, the observations, and the actions. The only thing left is to define the reward functions. The first function rewards the agent for moving forward. At this stage, our goal is not to maximize speed. Instead, we simply want to teach the algorithm that moving forward is significantly more beneficial than standing still. To achieve this, we use the following function, which maps the vehicle's speed to a reward value between 0 and 1. The remaining functions penalize undesirable behavior. The first and most important penalty concerns collisions. Every time the go-kart comes into contact with an obstacle, the function returns a value of -1, significantly reducing the cumulative reward. The next function concerns the use of the throttle and brake pedals. In this model, throttle and brake are represented by two independent output neurons. As a consequence, the model may decide to press both pedals at the same time, which is undesirable in most situations. The function compares the throttle and brake values. The more both pedals are pressed simultaneously, the larger the penalty applied to the model. The final function discourages aggressive steering. A sudden steering input can, of course, be necessary in racing situations. However, constantly making rapid and erratic steering corrections rarely leads to good performance. By measuring the difference between consecutive steering commands, the function applies an increasingly larger penalty as that difference grows. The reward functions related to forward speed and collisions define the primary objective of this experiment. The remaining two serve as auxiliary objectives. They do not determine what the agent should achieve, but instead help it develop a smoother and more stable driving style more quickly. That covers the basics. Of course, this overview barely scratches the surface of reinforcement learning. Its purpose was simply to explain, at a high level, how an AI model can be trained to drive a go-kart around a racetrack. But enough theory. It's time to see how the training process actually unfolded based on everything we've just discussed. At last, we can begin the actual experiment. Don't expect impressive results just yet. Before the model stops behaving randomly and starts making noticeable progress, let's take a moment to go over the information displayed on the screen. At the bottom of the screen, you'll find the standard vehicle telemetry, speed, engine, RPM, and the positions of the throttle and brake pedals. You'll also see the current lap information, although that won't be particularly important at this stage. In the bottom left corner, there are three additional panels. The first is the radar, where each moving dot and its corresponding line represent a single radar ray. Together, they create a simplified representation of the surroundings, which is fed into the model as one of its observations. Next to it is a map of the track, along with a marker indicating the kart's current position. The track gradually changes color from blue to red to visualize the speed reached in each section, although that won't become meaningful until later in the experiment. The final panel displays the kart's maximum speed statistics. The four values represent the highest speed achieved during the current lap, the previous lap, the best lap, and the entire experiment. In the top left corner, you'll see the current lap time. As soon as the kart completes its first full lap, the result will appear here. From that point on, the delta indicator will show how much faster or slower the current lap is compared to the best lap at the same position on the track. This makes it possible to estimate whether the current lap has a chance of setting a new record. At the top center of the screen are the progress bars for the current episode and the overall experiment. Each episode lasts for a predefined maximum number of simulation steps. Once that limit is reached, a new episode begins. The progress bar on the right shows the number of models generated during the experiment and indicates which one is currently being tested. However, seeing 61 models does not mean that only 61 episodes have been completed. Not every episode produces a model worth saving. The actual number of completed episodes is displayed above the progress bars. The final panel is the reward monitor. It provides a real-time visualization of when and why the model receives rewards or penalties. This is an extremely useful tool when testing and analyzing different reward functions. The ratio view shows the contribution of each reward function to the final reward. As training progresses, the contribution of rewards should gradually increase, while the contribution of penalties should decrease. This is one of the earliest signs that the model is beginning to learn the desired behavior. The values view displays the current numerical values of each reward function, along with a graph showing how they change over time. Now all that's left is to watch how seemingly random decisions gradually evolve into behavior that increasingly resembles deliberate vehicle control. Keep in mind that we're observing the model at the very beginning of its training. It doesn't know the track yet, nor does it understand the rules of its environment. Every mistake is simply another lesson. At the very beginning, we can see just how difficult it is for the early models to complete a full lap. Over time, the kart gradually starts to pick up speed, which increases the reward. However, the model still struggles to avoid collisions, and every corner seems like an impossible obstacle. As the speed increases, we also begin to see small improvements in steering, allowing the model to make it farther and farther around the track. Finally, after 220 episodes, the kart recorded its first complete lap. Let's take a look at that lap with the footage slightly sped up. Compared to the beginning of training, the progress is already clearly visible. The kart still moves very erratically, but at the same time, it manages to navigate most corners without crashing into the barriers. It's also quite clear that sharp left-hand corners are still its biggest challenge. After 250 episodes, the model is regularly completing full laps and setting new records. During this lap, it managed to break the 40-second barrier. It still struggles with tight left-hand corners, but I think that problem will soon be solved as well. Not long after, and another 90 episodes later, the model completes the entire track without any collisions and breaks the 35-second barrier. This run still lacks smoothness, but the improvement is clearly visible. Now we're waiting for it to break the 30-second barrier. We're watching runs that demonstrate the capabilities of each successive model, while the episode count continues to rise quickly. The previous 5-second improvement in lap time required 90 episodes. Now we've already gone through another 200 episodes, and the lap time hasn't improved by even 2.5 seconds. It's possible that the current experiment is approaching the limits of what it can achieve, but a later analysis of the results will give us a clearer answer. Finally, after 1,060 episodes, the model managed to break the 30-second barrier. So it seems that the model is still capable of finding a better policy and improving its performance, although it required significantly more time. After 1,335 episodes and 61 saved models, we decided to stop the experiment and analyze the results. Collisions still occur from time to time, and the racing line is far from optimal. However, the results had begun to stabilize, and further training with the current reward functions was no longer producing significant improvements. The resulting model provides a solid foundation for the next series of experiments, where we will place much greater emphasis on lap times and finding the optimal racing line. All that's left now is to summarize the experiment we've just completed. We can do this by analyzing a few graphs that show how some of the values we monitored changed as the experiment progressed. Let's start by looking at how the maximum speed changed. As the experiment progresses, we can see a steady, almost linear increase in speed. This is an expected result, since in this experiment, the value of the reward function depended on the kart's speed. The next graph shows how the cumulative reward changed over the course of the experiment. At the very beginning, we can see a period of stagnation, despite the kart's increasing speed. The reason for this is collisions, which I'll talk about in a moment. After this initial stagnation, the reward increased rapidly. During the same stage of the experiment, we also saw the kart set new lap records one after another. In the third part of the experiment, the growth of the cumulative reward earned by the agent begins to slow down again, with each improvement becoming smaller and smaller. At this stage, the agent had significantly reduced the penalties it received through more stable steering, fewer collisions, and more efficient use of the throttle and brake pedals. At the same time, further increases in the kart's speed no longer resulted in a noticeable increase in reward. Remember, in this experiment, we primarily rewarded forward movement rather than simply maximizing speed. As a result, the agent had essentially come close to the maximum amount of reward it could achieve, and continuing the experiment without making changes to the reward and penalty functions no longer produced any significant improvements. The next graph shows how much time the kart spent in collision during each consecutive episode, and this gives us the answer to why the cumulative reward did not increase at the beginning of the experiment despite the kart's increasing speed. The kart was getting faster, but it still couldn't effectively avoid collisions in the corners. This resulted in more frequent collisions and, consequently, greater penalties. Once the agent began navigating the corners more effectively, the time spent in collision started to decrease. During the second part of the experiment, it remained close to 0. The final graph shows the lap times achieved by the kart throughout the experiment. From the moment it completed its first full lap, every subsequent model was also able to complete a lap before the end of the episode. We can also see a clear downward trend in lap times, which began to level off as they approached the 29-second mark. Finally, let's compare the lap times achieved by a human driver and by our best model so far. In the case of biological intelligence, the best lap time was 20.5 seconds. This time was achieved on the 4th lap of the run currently shown on screen. Well, compared to the best time of just over 29 seconds achieved by one of our AI models, the difference is significant. We can also assume that, with enough practice, a human driver could improve this record even further and potentially set a lap time below 20 seconds. But let's not panic just yet. There's still plenty of room for improvement. The approach we've used to train the model so far shouldn't really be compared directly with the results achieved by a human driver. A human can see the full view of the track ahead and observe what lies farther down the road. This allows the driver to understand the nature of an approaching corner and plan a reaction in advance. The model receives a much more limited representation of its surroundings, built primarily from radar measurements taken in front of the kart. Let's run one more small experiment. Let's try to visualize what the track might look like from the perspective of the AI model. Once we translate this data into an image, it becomes clear just how much context is lost. Let's see how a human driver performs under these conditions. We can see a noticeable difference in the way the kart is driven. It seems that seeing the track this way requires the driver to be more cautious, which results in slightly slower lap times. However, the way the track is represented isn't the only factor we need to consider. Humans also have memory, and with every lap, they become more familiar with the layout of the track. Even with such limited visibility, a human can recognize a particular section of the track and still prepare for the appropriate reaction. Our current model, on the other hand, makes every decision based solely on its current observations and doesn't use any history from previous steps. This limits its ability to plan ahead. However, there are techniques that can provide the model with a form of memory as well. We'll focus on improving the model in future videos. I'm aware that reinforcement learning was covered only at a very general level in this video, so perhaps not everything is completely clear, or maybe some parts need further explanation or a deeper dive. Let me know in the comments. For now, thank you for watching. I'll see you in the next video.